Okay, good morning, Professor David J. De Los Reyes. Okay, it's October 12, 2023. The time is 4:02 a.m. It's good morning already, October 12. Okay, my topic for this session will be a continuation of my alternating current machines. It's under the long video format, and we are now on lesson number 37. We are now on lesson number 37. Okay, let's proceed. So for those of you who are following my channel on the topic easy machines, uh, let's continue with lesson number 37. Okay, lesson number 37. The, the lesson for this morning will be easy machines, lesson number 37, and the title of the topic will be example problem on stepping up, meaning it will be an application problem for stepping up voltages, okay, on the application of transformers. Okay, I will try to read the problem. Example problem. 3 with the ratio 10:1 transformers are connected delta Y for stepping up the 2300 volt three-phase source. Calculate the line voltage. Okay, let's try to bring out the figure. So it seems we are having an alternator in which the output voltage of the alternator is at 2300. Okay, and this output is fed to a transformer, which according to the problem it is for stepping up. So meaning to say the input voltage will be stepped up, okay? That's why the connection is delta to Y. Because under our discussion on the application of the different connections, delta to Y is actually for stepping up. So we could verify this morning if really the connection delta to Y is really for stepping up. Okay? Three-phase source. So it seems we are given an alternator here. 3 terminals are coming out, and this alternator is fed to a transformer which is a step up. So it will be connected like that. And what comes out on the output side of the transformer will be a voltage line to line equal to. Okay? The problem says that if the output, if the source voltage is 2300, okay, what will be the line to line voltage of the output of the transformer with the given condition? The ratio transformation is actually 10:1. Meaning to say, if you got 2300 here, what will come out? For it to be step up, it will be 2300 times 10. That's the meaning of this. That's why it's step up. Right? The problem is asking what will be the terminal voltage here. Will it go up? Of course it will go up because the problem says for stepping up. And under our study or the concept for the application for a delta to Y connection is actually for stepping up. Okay, let's try to bring out the figure. The figure will be something like this. The connection of the transformer is actually delta on the primary. On the secondary side, it is Y. And according to the specification of the problem, the source voltage is 2300. The voltage coming out from the alternator is 2300, meaning the line to line voltage. Okay? So if the connection on the primary will be delta, okay, if the line if the line-to-line voltage is 2300, for a delta, the line-to-line voltage is actually equal to the phase voltage. So if this is 2300, am I still on the camera? 2300. The voltages for each phase, okay, for the connection delta will be 2300. This is 2300, 2300, and this is 2300. So we almost solved the problem halfway already, because we are going to the side of the secondary, because the the problem is if the applied voltage is 2300, or meaning the output of the alternator is 2300, what will be the voltage that will come out on the secondary of the transformer? The connection is Y. Okay, so this is, the primary is delta, the secondary is Y. The problem is asking what will be the voltage across the line. And what's the significance of this voltage here? Why we need to step it up? Oh, it is something like this. If we got a power plant over here, okay, and we must have to deliver power to the customers, okay, that voltage 2300, if you try to deliver this 500 miles away, this 2300 volts will get lost. Some part of it will get lost on the transmission line, because the length of the transmission line is just for example 500 miles. Maybe this 2300, if the size of the wire is not so big, maybe we are lucky enough if we got the 1000 volts 500 miles away. So to compensate for the losses of the transmission line, we must have to increase this one first. And the way to increase this one is actually to step up this voltage to a higher voltage. Okay? So when we step up this one and we feed it to the transmission line, okay, the value should be high enough. Right? So when it reaches the customer side, there is still a big amount which could be stepped down to a value 120, because if this is 2300, like what I said, if the length of the transmission line is 300 miles away from the customers, the voltage will be minimal already, and we could the customers might complain because the voltage going to their premises is too low. So we need a high voltage. So this 2300, we step it up to be fed to the transmission line. So 500 miles away, of course, even if you lose 10,000 volts over here, there will still be 30,000 going to the primary transformer on the distribution side. So that's the purpose of stepping up the output of the transformer, okay, before it will be fed to the transmission line. So the purpose for step up transformer is for feeding up to the transmission line. Okay, let's try to bring out the solution. What is given is 3-to-1 ratio, right? The meaning of that, the value A will be 10:1, or the ratio transformation is actually 10. Okay, step up. So meaning to say, if we got 2300 here, if we try to refer it to the secondary, we should multiply it by 10, right? Step up. And according to the given problem, capital letter B with the subscript P, again with the subscript LL, the meaning of this, the primary voltage or the phase voltage, or primary voltage, sorry for this one, this P here refers to phase value, phase. The phase voltage, okay, is actually equal to the line-to-line voltage, and this is equal to 2300. Why is this so? Because the connection is delta. The line-to-line is 2300, and for a delta, the line-to-line is equal to the phase voltage. That's why I place it here. B sub P, again with the subscript LL, is equal to 2300. The problem is asking what will be the value of B sub S line to line, with all the given specification. The voltage that will come out here before it will be paid to the transmission line. Okay? Okay, let's try to bring out the solution. For delta connection, okay, the primary voltage line to line is equal to the primary voltage phase value. We are comparing line to line value with respect to the phase value. This subscript here refers to primary. Okay? For a delta connection, the value of the line to line voltage is equal to the value of the phase voltage. Okay, considering primary connection. Okay, we are on the primary side. So this P here refers to primary. Right? And to compute for the voltage of the primary phase value, this should be equal to the line to line. The output of the alternator is 2300 on the line. So the value of the phase voltage on the primary will be 2300 volts. It is this. If this is 2300, each of the arm will be 2300 because the connection is delta. Right? At least we know the relationship of the voltages for a delta connection. The line-to-line voltage is equal to the phase voltage for a delta connection. Okay, no matter what happens in this world, that concept will remain unchanged. Okay, for step-up transformer, the ratio of transformation is actually Vs. What's happening? My pen is dried out. Vs over Vp. For step up, because originally what we are using is a ratio transformation is actually Vp over Vs. This is for step down. Okay, but the transformer is a step up, so we will reverse this one. Okay, the numerator will now be Vs and the denominator will be Vp because this is a step up. Right? This was the original one we are using because all the problems we are solving were step down, and the ratio of transformation is actually Vp over Vs for step down. But for step up, ratio of transformation is actually Vs over Vp. We use phase values. It's not the line-to-line values, right? Phase. So if we try to compute for the primary voltage phase value, okay, what will come out? Now, secondary, it will be this value here, phase value times A. Okay, so the secondary voltage phase value, we are now on the secondary side on the Y connection. It should be A times the primary voltage phase value. This should be 10. The primary voltage phase value is up as per computation is 2300. Because this is 2300, the phase voltage will be 2300. So the one we are talking of phase value on the primary is actually the 2300. So this is 2300. So the phase value on the secondary, if it is a step up, it will be 23,000 volts. It really goes up. That's why it is step up, right? So meaning to say this is 2300. If we refer this to the secondary, okay, and according to the problem, the transformer is a step up and it got a multiplicand of 10. So if this is 2300, the phase voltage on the secondary will be 23,000. This is 23,000 volts. And for a Y connection, like what I derived the last time around, the line-to-line voltage relation of for a Y connection, the relationship between the line-to-line voltage and the phase voltage is actually given by this equation. That is, the line-to-line voltage is square root of 3 times the value of the phase value, times the value of the phase voltage, phase value of the voltage. So if I will now try to place the proper subscript B sub S line to line, meaning to say the line-to-line voltage on the secondary should be equal to the phase value times square root of 3. So this should be square root of 3. Okay, so don't ask me where that square root of 3 emanates. We derived this one the last time around. That is standard for a Y connection. The relationship of the line-to-line voltage with respect to the phase voltage is by the factor square root of 3. So if we are given the phase value to be 23,000, the line-to-line voltage should be square root of 3 times 23,000, and this is 39,837 volts. Okay, so after stepping up, what is being paid to the transmission line is 39,837 volts. And I think this is more than enough. If this voltage will travel 500 miles, okay, I think we could not lose 10,000 volts across the line. Maybe 2,000, 3,000, we lose it on the wastage on the line. So there will be more than enough voltage to power up the customers. Okay, okay guys, this is a good example for the problem for stepping up problem. Okay, and the transformer that is needed for stepping up is actually the delta to Y connection, because a small voltage on the primary, if we try to use the delta to Y connection, it will go up. This 2300, upon reaching the secondary of the transformer, it will now be equal to 39,837 volts. Okay, that's it guys. This is Professor David G. De Los Reyes. Good morning from Los Angeles. This is a problem on the stepping up, and the connection is delta to Y. Good morning.